Alright, in this video we're going to take a look at Le Chatelier's principle, and we'll go through some various examples of trying to explain what happens when stresses are applied to equilibria. So just remind yourself of what Le Chatelier's principle actually states. It's worded slightly differently in different textbooks, but if you have a system that is at equilibrium and you apply a stress or some kind of disturbance, the system is going to shift either forwards or backwards in order to reduce that stress, okay, to alleviate the stress. If we have an equilibrium that shifts in the forward direction, remember that the forward direction, you have reactants on the left and you have products on the right. So if you have a forward shift in equilibrium, you're going to be producing more products and therefore using up your reactants. So the concentrations of any aqueous or gaseous species on the left will decrease. The concentrations of any aqueous or gaseous species on the right will increase in a forward shift. In a reverse shift, it's just the opposite situation. Now we said if you have a system at equilibrium and you apply a stress, well, what are some stresses? From your kinetics unit, these are basically the things that affect the rates of reactions. These are factors that affect rates, because equilibrium is all about equal rates for the forward and reverse reactions. So if we change the temperature of the system, if we change any concentrations within the system, if we change any pressures, if there are gases present, okay? Now, remember, one very important point is that liquids and solids have constant concentrations. If you have half a glass of water and I have a full glass of water, I have twice as much water, but the concentration of water in those two situations is exactly the same. So concentration of a liquid or a solid is constant, and that's why we don't include them in the Kc expression, and therefore adding or removing liquids and solids has no effect on an equilibrium. It doesn't act as a stress. So let's look at an example of a reaction at equilibrium. So here is a heterogeneous equilibrium. It's heterogeneous because there are gases and solids present. If this was all the same phase, if these were all gases, we'd have a homogeneous equilibrium. So when you have different phases, it's called a heterogeneous equilibrium. So we're told that this reaction is endothermic, which means in the forward direction, heat is being absorbed. Some teachers would then write the word heat on the left side of the equation. You don't really need to do that, but if it helps, you can do that. And it's happening in a closed, rigid vessel. You cannot have an equilibrium system unless it's a closed system. The reactants and products cannot be allowed to escape. So if there are gases present like this, the vessel must definitely be a sealed or closed vessel. The fact that it's rigid simply tells us that the volume of this container won't change. So it's not going to expand or contract. The volume is constant. Now the question is going to ask us to focus on the amount of SO3. Notice the word amount. So the moles, the mass of SO3. What's going to happen to that if we perform these various stresses? Well, we notice that SO3 is here on the left-hand side of the equation. So what would make the SO3 increase? Well, a reverse shift would cause an increase of SO3 because we'd be producing more SO3. On the other hand, a forward shift would use up some of the SO3. In a forward shift, the reactants get used up and the products get produced. So if this equilibrium shifts backwards, we're going to make more SO3. If it shifts forwards, we're going to end up with less SO3. So what happens if CO2 is added to the system? I'm going to try to give you two different explanations here, both of which are acceptable for the AP exam, and they both avoid using anthropomorphic language. We're going to try to avoid talking about the system or the reaction wanting to do something. The system doesn't want to do anything. It has no emotions, right? So we have this, now one point before I jump in. Many students will mistakenly claim that CO2 is being added, and they look at the equation, they see CO2 on the left side of the equation. They want to say something like CO2 is added to the left side of the equation. That is wrong. You're not adding CO2, you're not removing oxygen, you're not adding CS2, you're not heating or cooling one side of an equation. You're doing these things to the vessel, to the container, to the system. So we're adding CO2 not to one side or the other of the equation, but we're adding it to the flask, to the vessel, to the system. So what happens if we add more CO2? There's two explanations that are acceptable. One is based on the reaction quotient, Q. Remember that if you're at equilibrium, which is how we started, Q is equal to K, or Kc if you want to talk about equilibrium constants with concentrations. So we start off with this expression for Q. This is just the equilibrium expression for this reaction. We've left out CS2 because it was a solid. So we have extra CO2 added to the system. Well, the CO2 is here in the denominator of Q. So what you would argue is that increasing the concentration of CO2 will cause Q to decrease. If you increase your denominator, the fraction gets smaller. So you'd start by saying increasing the CO2 concentration causes Q to get smaller. Therefore, Q is now less than Kc. If Q is less than Kc, we're not at equilibrium anymore. How do we get back to equilibrium? Well, Q is going to have to increase. If it's less than Kc, Q will have to get bigger. How can a fraction get bigger? Well, you're going to need more products, and you're going to need less reactants. More numerator, smaller denominator, and your fraction will get bigger. So in this situation, we're going to end up making more oxygen, and we'll have less SO3 in the vessel. In other words, we ended up shifting forwards. Now, rather than go through all that reasoning about Q, if it's smaller than Kc, Q must get bigger, you can simply memorize, if you haven't already, that when Q is less than Kc, that creates a forward shift. For the reasoning I just laid out, Q will have to get bigger, and if Q is to get bigger, we need more products and we need less reactants. That would be a forward shift. If Q is equal to Kc, then there is no shift. You're at equilibrium. And the third situation, if Q is bigger than Kc, you get a backward shift, or a reverse shift. And the reason there is that Q is now too large, so Q is going to have to get smaller. For Q to get smaller, we need less numerator, less products, and we need bigger denominator. We need more reactants. So less products, more reactants would be a reverse shift, a backward shift. So memorize these three situations. Now there's another way to explain what happens. So we said here that if you add CO2, Q will get smaller. Q is then less than Kc. A forward shift occurs, and if the reaction shifts forward, you'll have less SO3 in the container. The other explanation is based on kinetics, okay, based on rates. And it goes something like this. You'd say, if you add CO2, now CO2 is a gas, and it's a reactant in the forward reaction. So we'd say concentration of CO2 increases, which causes the forward rate to increase as well. Okay, the forward rate increases. Now why is that? Because CO2 is a reactant in the forward reaction. And we remember from our kinetics unit that if you increase the concentration of reactants, you'll increase the rate. So therefore, the forward rate is now greater than the reverse rate. They used to be equal at equilibrium. Now the forward rate is greater than the reverse. If the forward rate is greater than the reverse rate, therefore you get a forward shift in equilibrium. In other words, you end up making more products and less reactants. Therefore, the concentrate, or the amount, we'll just say, of SO3 decreases. All right, so there's the kinetics explanation. And so on a free response question, you can use either the kinetics explanation or the reaction quotient explanation. But please be familiar with both. Be comfortable using both. What happens if we add some more CS2? Now, you can pause the video and try that yourself if you like. Add some more CS2 to the flask. All right, now did you notice that the CS2 is a solid? Okay, because it's a solid, its concentration doesn't change. So using the kinetics explanation, we would say something like adding more CS2 does not change its concentration because the CS2 is a solid. Therefore, neither the forward nor reverse rate is affected. Therefore, the system stays at equilibrium. That would be a good kinetics explanation. Notice it's also easy to explain this using the reaction quotient. We start off again that Q was equal to Kc before the stress, and then we've added some CS2. Well, the CS2 is not in the expression for Q, and adding CS2 does nothing to these concentrations, therefore it does nothing to Q. Q is still equal to Kc. There's no shift in equilibrium. Nothing happens to the amount of SO3. So there's two different ways to explain that. All right, so here's two more stresses. Pause the video and see if you can explain what happens if oxygen is removed. So using a kinetics approach, we'd say removing oxygen decreases its concentration. Therefore, that will slow down the reverse reaction. Oxygen is a reactant in the reverse reaction. So the reverse rate slows down. Now the forward rate is greater than the reverse rate, and so we get a forward shift. A forward shift means there'll be less SO3 in the container. How's that? Using the expression for Q, we can also explain this in this way. We'd say if you're removing oxygen, you're decreasing oxygen's concentration. Decreasing oxygen's concentration, where it's in the numerator, will cause Q to get smaller. If Q is now less than Kc, there's going to be a forward shift in equilibrium, and you'll end up with less SO3 in the container. Now, one word of caution here. We're focusing in these questions on the SO3. What happens to everything else in the system? Well, if you've removed oxygen, we just decided that will create a forward shift. So you're going to end up losing CO2. You're going to have less CO2 when the new equilibrium is reached. You're going to have less SO3 in the container. Now their concentrations will drop and their amounts will drop. What about CS2? Well, its concentration doesn't change because it's a solid, but you will get more CS2 in the container. If there's a forward shift, the amount of CS2 has to increase. You can't make more products in this reaction unless you make more CS2 as well. So the grams or the moles of CS2 will increase, but its concentration does not because it's a solid. Now what about oxygen? We started by removing some oxygen, and then shifting forward, we're going to make more oxygen. But when the new equilibrium is reached, we will not have achieved the same concentration we had before we removed oxygen. So because we removed oxygen, in the new equilibrium, there's going to be less oxygen in the container. There will be more oxygen than immediately after we removed it, but there will be less oxygen than there was in the original equilibrium. Same thing back here. If we added CO2, the system's going, the reaction we said would shift forward to get rid of the extra CO2, but when the new equilibrium is reached, there's still going to be more CO2 than there was before we added some. If you added CS2, well, it's a bit different because there was no shift in equilibrium there. What happens if we heat the vessel? This one's a little bit more complicated. If you heat the vessel, we have to learn something new or remind ourselves of something new. There's two situations, and it depends on whether the reaction is endothermic or exothermic. And I'm trying to look back here. The original sheet told us that this was an endothermic reaction. So for endothermic reactions, and this is something you want to memorize, for endothermic reactions, if you raise the temperature, you will raise Kc. Increased temperature increases Kc. Decreasing temperature decreases Kc. For an exothermic process, it's the opposite. So for an exothermic reaction, if you raise the temperature, you will decrease Kc, or you'll lower the Kc value. So be sure you memorize that. If you raise temperature in an endothermic process, Kc gets bigger. If you lower the temperature for an endothermic process, Kc gets smaller. For exothermic processes, it's the opposite. Raising temperature lowers Kc, lowering temperature increases Kc. So if we've heated the vessel, and we see that this was an endothermic process, the original sheet said it was an endothermic reaction, then raising the temperature is going to raise Kc. So what we would say if we were arguing from a Q perspective is that Kc has been raised because the reaction was endothermic. Kc is larger. Therefore, Q is now less than Kc. If Q is less than Kc, as we've seen before, there'll be a forward shift in equilibrium. You'll end up with less SO3 in the container. Now, what about from a kinetics perspective? Heating the vessel, we know from kinetics, will increase the rates of both the forward and reverse reactions. However, the endothermic direction, its rate increases more than the exothermic direction. So when you raise the temperature, both the forward and reverse rates will increase. You should say that. However, the endothermic direction, in this case the forward direction, will increase its rate more than the exothermic direction. So basically the forward rate increases more than the reverse rate. Therefore, there'll be a forward shift in equilibrium and we end up with less SO3. If we had cooled the system instead, then the endothermic direction slows down more than the exothermic direction. And so the forward rate would have slowed down more than the reverse rate. And now the reverse rate's larger than the forward rate, there'll be a reverse shift in equilibrium. What happens if we decrease the volume of this vessel? Decrease the volume of the flask. Now we started by saying it was a rigid vessel, but let's imagine that we've taken the contents and we've transferred everything from this vessel into a smaller container. So we're decreasing the volume. What happens to the amount of SO3? Well, you can explain this again using Q or using kinetics. Let's do Q first. If you've squeezed everything into a smaller volume, the volume's decreased, we know that that means every concentration of a gas or of of gases, not aqueous species, gases, would increase. You've got a smaller volume, you're going to have higher concentrations for everything in the container, all the gases. So what does that do to Q? Well, the numerator and denominator will be larger. However, if we look at the overall orders for the numerator and denominator, the numerator is raised to the power of 4. The denominator has something raised to the power of 1 and something being squared, which means the numerator essentially is 4th order, while the denominator essentially is 3rd order. So now increasing both the numerator and denominator is going to have a bigger effect on the numerator. So we'd end up saying, for this question, we would say, lowering the volume raises all the concentrations. They all increase, all these gases increase, but the numerator in the Q will increase more than the denominator because it's 4th order versus 3rd order. Therefore, Q gets larger, therefore Q is bigger than Kc, and that will create a reverse shift. What about from a kinetics perspective? Well, from a kinetics perspective, we'd end up saying that if you've increased all of the concentrations by lowering the volume, that's going to increase the forward rate and the reverse rate. But do they increase equally? If you think of the rate law for the forward reaction, we'll just assume for this argument that it's an elementary process. You'd say that the rate is equal to a rate constant times CO2 times SO3 concentration squared. And for the reverse reaction, this is forward, for the reverse reaction, rate would equal, we'll leave out the solid, it's equal to rate constant times concentration of oxygen to the power of 4. Now those rate constants are different. This would be the forward rate constant, that's the reverse rate constant. And we would use almost the same logic. We'd say both rates will increase because the concentrations of everything in these two rate laws has increased. However, the reverse rate is going to increase more than the forward rate because it's 4th order, while the forward reaction is 3rd order overall. So the reverse rate increases more than the forward rate, and that creates a reverse shift in equilibrium. What happens if we add a catalyst? Well, adding a catalyst has no effect on the equilibrium. It increases the rates of the forward and reverse reactions equally, and therefore they were equal. The rates were equal before the catalyst was added. The rates are equal after the catalyst was added. If the system happened to not be at equilibrium and you add a catalyst, that'll simply make it reach equilibrium faster. But when it reaches the equilibrium, the concentrations will be the same as they would have been without the catalyst. Catalysts speed up the reactions. They don't change the amounts of products you'll make. What about from a Q perspective? Well, the catalyst doesn't change any of these concentrations, so there's no effect on Q. Therefore, Q is still equal to Kc. Okay, we'll look at two more stresses with this equilibrium. What happens if we add some helium? Helium, we know, is an inert gas. It's a noble gas on the periodic table, so that means it doesn't react with anything in our system. But it does, of course, add one more gas to the container. What's going to happen if the volume is held constant? Well, if the volume is held constant, then adding helium is going to have no effect on this equilibrium. From a Q perspective, you would argue that adding the helium doesn't change any of these concentrations because the volume was held constant. There is an extra gas, so the total pressure goes up, but we know from Dalton's law that the total pressure used to be the CO2 pressure, the SO3 pressure, and the oxygen pressure. So the total pressure is going to go up because now there's an extra gas. There's some helium gas. But the pressures that were already there don't change. The total pressure changes, but none of the partial pressures change. And again, that's because the volume is held constant. So what you could argue from a kinetics perspective is that because the helium doesn't change the volume in this case, none of the concentrations will change of the gases. Therefore, the rates of the forward and reverse reactions are unaffected. There's no shift in equilibrium. Now, if you were to add a noble gas, this time we'll use argon, but it really doesn't matter, another noble gas, but this time under constant pressure situations. Now, how would that be done? Imagine fitting our flask with a movable piston. So now we've got a piston attached here, and this piston can move up or down. So what's going to happen now, if we add some extra gas, some argon gas in this case, the piston is going to move upwards. It's going to expand. And that's because the pressure inside the flask is now larger than the pressure outside the flask. So the piston will have to move upwards until the pressures are again equal. So the final pressure when the piston stops moving is going to be the same as the pressure was before the gas was added. It'll be equal to the outside air pressure. But to do that, to maintain that constant pressure, the volume has to increase. So if the volume does now change, if the volume increases because of the extra gas, then all of our concentrations will change. And we would just use the same reasoning we used earlier. The volume increases, all of the concentrations will get smaller. Because the numerator here is fourth order, the numerator in the denominator is only third order, the numerator will get smaller at a greater rate than the denominator. So the numerator is going to be more affected. That's going to make Q smaller, and therefore Q is now less than Kc. There'll be a forward shift. From a kinetics perspective, you'd argue that the only way to have constant pressure with an extra gas is to increase the volume. That lowers all the concentrations of the gases. That will decrease the rates of both the forward and reverse reactions. If you look at the rate laws again, it's third order and fourth order, so the reverse rate will lower more than the forward rate, and therefore a forward shift occurs. We'll go through this one a little bit faster. Pause the video and see if you can predict what will happen to the amount of chlorine in this equilibrium happening in a rigid closed vessel. There's delta H. That tells us that this reaction, because it's negative, tells us that the reaction is exothermic. The last reaction was endothermic. So pause the video, see if you can predict what happens to the amount of chlorine based on these stresses, and try to use a good explanation when you do that. So the first one, if we cooled the vessel, that's going to change Kc. This reaction is exothermic. When you lower the temperature for an exothermic reaction, Kc gets larger. Therefore, Q is now less than Kc. Q smaller than Kc will result in a forward shift, and that means we're going to get more Cl2. From a kinetics perspective, you could say that the rates of forward and reverse reactions are going to decrease with the cooled temperatures. However, the endothermic direction, in this case that's the reverse direction, it slows down more than the forward reaction does. So if the forward reaction is now faster than the reverse reaction, we still get a forward shift and more chlorine added. What happens if you add some oxygen? Well, oxygen is a gas, so adding oxygen increases its concentration. Here's the expression for Q for this reaction. Increasing oxygen concentration will cause Q to get smaller. Q is now less than Kc. That creates a forward shift, and therefore we get more Cl2. From a kinetics perspective, you'd say increasing the oxygen causes its concentration to increase. That will increase the forward rate of the reaction. The forward rate is now larger than the reverse rate. Forward shift, more chlorine. What happens if we add some water? Well, water here is a liquid, and so the water does not appear in the Kc expression and doesn't affect any of these other concentrations. Now, if this were an aqueous equilibria, if things here were dissolved in the water, then adding more water would cause all of the concentrations to decrease. But this reaction is happening in a flask with gases and there's a little bit of liquid water at the bottom of the flask. So adding a little bit more water or taking out some water isn't really going to change any of the concentrations of the gases that were there. So the added water does nothing to Q. Q is unaffected, so the system stays at equilibrium. There's no shift. From a kinetics perspective, you'd argue that because the water is a liquid, its concentration is constant, therefore adding water does nothing to the forward or reverse rate, and therefore there's no shift. Remove some HCl. Well, if you remove HCl, you're lowering its concentration. Lowering the concentration of HCl will cause Q to get larger because HCl is in the denominator. So if you have a smaller denominator, you get a larger Q. So Q is now bigger than Kc. We're going to shift backwards as a result, and shifting backwards, there'll be less Cl2 in the container. From a kinetics perspective, you could argue that if you've removed HCl, you've lowered its concentration. That will take the forward rate and reduce it. So if you have a smaller forward rate, the reverse rate is now larger than the forward rate. You get a reverse shift and less Cl2 in the container. Adding a catalyst. The catalyst has no effect on equilibrium, although it speeds up both the forward and reverse rates. It speeds them up equally, so therefore there's no shift in equilibrium. Helium is added to the rigid flask, so we'll assume that means the volume is held constant. If the volume is held constant, adding helium does nothing to the concentrations of any gases that were there. Therefore, Q is unaffected. Q is still equal to Kc. There's no shift. You could also say that none of the concentrations are affected because the volume is held constant. Therefore, the rates of the forward and reverse reactions remain equal. There's no shift. If you transfer the contents of this flask to a larger vessel, well, now the volume has increased, so all of the concentrations will decrease. The numerator here is second order, the denominator here is fifth order. So if you decrease all of the concentrations, the denominator will decrease more than the numerator, to the power of 5 versus to the power of 2. So if the denominator decreases more than the numerator, Q is going to get larger. If Q gets larger, there'll be a reverse shift. From a kinetics perspective, you'd say that this increased volume causes all the concentrations to drop. That causes the rates of the forward and reverse reactions to drop. Because the forward rate is fifth order, the reverse rate is only second order. Notice I'm ignoring the liquid when I talk about that. The forward rate will decrease more than the reverse rate. Now the reverse rate's larger than the forward rate, you get a backward shift. One more. Pause the video and see if you can predict what happens to the amount of iron in the system. Here's the iron if we perform these various stresses. So we're going to remove some hydrogen. Removing hydrogen lowers hydrogen's concentration. That's going to cause the forward rate to decrease. If the forward rate decreases, now the reverse rate must be larger. That will create a reverse shift. And if it shifts reverse, there'll have to be less iron in the container at the new equilibrium. Now notice I'm not saying that the concentration of iron will be less, because we know it's a solid, so its concentration doesn't change. But the amount of iron, the mass or the moles of iron, will have to be less because there was a reverse shift. Now if you look at the expression for Q here, leaving out liquids and solids, Q is equal to the concentration of water to the power of 4, water is a gas in this reaction, over concentration of hydrogen to the power of 4. So if you were to remove hydrogen, you're lowering hydrogen's concentration. That will cause Q to get larger. Q is now bigger than Kc. A reverse shift occurs. Therefore, less iron. If you add iron oxide to the flask, well, the iron oxide is a solid. It doesn't appear in the expression for Q, therefore adding some iron oxide does nothing to these concentrations. Q is not affected, there's no shift. You could also argue that because it's a solid with constant concentration, the rates are unaffected, therefore the forward-reverse rates remain equal, there's no shift. Let's cool the flask. Well, we know this reaction is endothermic. So cooling the flask for an endothermic reaction causes Kc to decrease. Kc decreases. If Kc decreases, then Q is now larger than Kc, therefore there'll have to be a reverse shift. A reverse shift means less Fe will be in the container. From a kinetics perspective, we'd say cooling the system slows the forward and reverse rates. However, the endothermic direction slows down more. So because the reaction as written is endothermic, the forward reaction slows down more than the reverse reaction. So the reverse reaction will cause, there'll be a reverse shift as a result, and you'll get more iron oxide, you'll have less iron in the container. Add some water vapor to the container. Water vapor is here. If we add some water vapor to the container, the Q is going to get larger. Higher concentration of water will cause Q to get larger. That means Q is bigger than K. A reverse shift will occur. From a kinetics perspective, increasing water vapor concentration will increase the rate of the reverse reaction. Therefore, you'll have a faster reverse reaction and a backward shift. You'll get less Fe in the container. If we fit the flask with a movable piston, so now its volume can change as we saw earlier, and we add some argon gas, what's going to happen? Well, we have constant pressure in the situation. The only way to have constant pressure would be for the piston to move upwards. If you add an extra gas, the volume is going to have to increase. If the volume increases, all of the concentrations will decrease. Now, looking at Q is fourth order in the numerator and fourth order in the denominator. So in this situation, Q would be unaffected because the numerator and denominator would both decrease equally. So the ratio for Q would stay the same. Therefore, Q stays equal to Kc, there's no shift. From a kinetics perspective, you'd say that increasing the volume of the container in order to maintain constant pressure will lower all of the concentrations. That will slow down the forward and reverse rates. But because the forward reaction is fourth order and the reverse reaction is fourth order, notice we're omitting the solids when we discuss that. The forward and reverse rates would slow down equally, and therefore the system remains at equilibrium. There is no shift that occurs. So there we have it, several examples of Le Chatelier's principle. You don't need to explain each of them with both the explanation for Q and kinetics. You can use either one of those explanations on a free response question, but please be sure that you're comfortable explaining things both from a kinetics perspective and forward and reverse rates, as well as from a perspective of the reaction quotient and a more mathematical way of looking at it.